Okay, good afternoon. My name is Joana, and today I'll be giving a presentation entitled Beyond Static Learning, Continual Learning is the Way. So, as some of you may know, in the medical domain, clinicians and radiologists are exposed to a great amount of data, such as images and reports. And the analysis of this data can be in search for suspicious anatomic structures or disease prediction, can be time-consuming and in turn transform into an error-prone task. That's why we have our deep learning approaches that have demonstrated their potential in numerous tasks of the medical domain, such as object detection, segmentation of anatomic structures, and malignancy prediction. So here's where the problem begins. Most of these methodologies were developed considering that the training data is representative of the target population of the problem we're trying to solve, and also under a statistical paradigm, meaning that we have our data, we developed a model, hopefully we will deploy it into a real-world application, and basically these models will be conditioned by the data given at a unique instant in time. At first sight, this would be okay until we realized, and I think some of you have already experienced this working with the medical domain, that data is the primary problem. Collecting a data set that is large and representative can be difficult. We can have misrepresentation of the target population, and this condition at some extent can be natural, take into account that some of these data sets are a result of a specific data set in a certain region of a specific country under specific conditions. Then we also have class imbalance, that once again can be a natural problem. Also, at some extent, if we talk about, for example, class diseases, and this is only natural, taking into account that some diseases are more prevalent than others, and where the disease more likely it is to be misrepresented. And finally, as I mentioned before, obtaining high quality label data is a really hard task. Apart from all these challenges, we still have the future-related challenges. One of them is new imaging acquisition protocols or machines that can emerge, and the other are new diseases that can appear, and COVID-19 is an example of that. And I think, for example, our colleagues of the biometrics field can confirm this. Okay, and so we saw that the primary problem lies in the data and their lack of variability. This is an inherent problem of the medical domain, and as such, the model should be aligned with this reality. Models developed as statistical paradigm do not have that ability, and so as humans, because we have the ability to continually acquire knowledge, because of that, a new paradigm arises, designated continual learning. The continual learning paradigm concerns models with the ability to continually acquire novel knowledge while retaining previously acquired information. And how this basically works is that we have a real-world application. We get data from that application that we are going to develop a model, and then that model is deployed to the real-world application. And this is a cycle, and the cycle begins again, and so on. Before introducing the main continual learning methodologies, I thought of introducing some concepts and metrics just so you could understand some basics. So let's start with the basic, and that is what to call this paradigm. And I believe you already know what is going to be the first one, right? So we have continual learning, but then we can also call it lifelong learning, incremental learning, and finally we have continuous learning that you can use it, but it's not so common in the AI field. Now going to the continual learning scenarios. Because we have a continuous stream of data and according to the order and type of data and the restrictions in each learning moment. And in this case, I define a learning moment as the cycle of the continual learning paradigm in data, training, and then deployment. There can be different continual learning scenarios. We can have test incremental, domain incremental learning, class incremental learning, and new classes and instances, also known as class incremental with repetition. So starting with the test incremental, and here I just they're basically, it really depends on the problem one is trying to solve that is going to basically change the scenario we are working on. And in this case, just to facilitate and illustrate the scenario, so I chose the classification problem where we have to identify fruits. And in this case, in the test incremental, what happens is that in each learning moment, the model is exposed to one task at a time. So in the first task, we have apples and bananas, and the model will have to try to distinguish between class 1 and class 2. And then in learning moment, in the second learning moment, we have task 2. And then once again, it will have to distinguish between one class and the other. Tests can be of the same type, meaning that we can have as we can see in this example, that tests are all classification, and there is no test repetition, meaning that if in this case we have in the first learning moment, the model is exposed to bananas and apples, and so in subsequent learning moments, the model will not see this type of data ever again. And so at inference time, basically with the task ID given, we will have to answer which class is it? Is it from class 1 or is it from class 2? Then we're going to the domain incremental scenario, and in this case, in the first learning moment, the first experiment, all classes are available, and then in subsequent experiments, only new instances of those classes are introduced. And in this case, this is a specific question. I adapted this from the paper, and Guido is one of the authors, where they basically just did it. They did this with the Manish, with the digits data set, and that was the question. So even after a certain experiment, after training, then we have considered that we have considered these labels, right? That we have apples, oranges, and strawberries are of class 1, and then we have bananas and cherries and pineapples are of class 2. And so basically, in this scenario, we just have to answer, given a fruit, which category is it? Is it from class 1 or class 2? Then we have class incremental, and in this case, it's a little bit similar to test incremental in the sense that we don't have class repetition. In its learning moment, the model is exposed to one class at a time. So in this case, we'll see apples, and then we'll see oranges, and then cherries. And there's no class repetition, meaning in subsequent experiments, we will not see this data ever again, at least for training. And so at inference time, the question in this case is, which class is it? So in this case, we will have to say, it's not a case of, is it class 1 or class 2? We will have to say, what is the category what is the fruit? And finally, we have the new classes and instances, also known as class incremental repetition. This one is similar to the one we saw just now. In the first experiment, the model may be exposed to one class or some classes, and then in further experiments, new instances of the classes seen before or new classes can be introduced. And so in this case, we do have the repetition. Now let's go to the metrics. We know that in the AI field, to measure the performance of developed models, we have metrics like accuracy, prediction, dissimilarity, coefficient score. But in this continual learning field, it is important also to have metrics that will measure the capability of the methods to transfer knowledge. And so before starting explaining these metrics, let's just imagine that we have a data set A that will correspond to this past data, and the model will be trained on data set A, and then we will have access to a data set B, and that will correspond to the new data, and the model will now be trained on data set B. So with backward transfer knowledge, what we are measuring is how much learning from the new data, the data set B, will impact the performance that the model has regarding the past data, the data set A. So this is backward transfer. Then we have the opposite, that is forward transfer knowledge. And in this case, we are measuring how much the fact that the model already learned from dataset B will influence the learning with the dataset B. And in this case, in order to measure this, we also need to train a model solely on dataset B in order to compare the differences in performance to see how learning from dataset B from past data had an influence, if it was positive or negative. Then we have another two metrics. We have remembering. This is pretty much related with backwards transfer knowledge. As the name suggests, it basically indicates if the model has a capability to remember past learned data. And so it could correspond to, it could be seen as a positive backwards transfer knowledge. And finally, we have forgetting, that it could be somehow redundant, because if we have remembering regarding some data set, then we won't have forgetting. Forgetting is pretty much the opposite. It measures the level of forgetting regarding past data, and it can be seen as a negative backward transfer knowledge. Now, finally, moving to the continual learning methodologies. Most continual learning approaches seek to mitigate the catastrophic forgetting effect, a phenomenon characterized by old knowledge being overwritten with the acquisition of new one. And we basically have three main fronts of action: regularization, dynamic architectures, and experience replay. Starting with regularization, one of the core ideas behind these techniques is the plasticity consolidation dilemma, in which there must be a trade-off between plasticity that will allow the combination of new knowledge and the consolidation that will protect the old one. And so basically with the regularization, we can have regularization at different levels, at the parameter space and at the feature prediction space. At the parameter space, what we basically do is, after training on a certain data, we will basically assign an importance weight to each parameter of the network. And basically, if the more important that the specific parameter is regarding the past data, the more protected it will be. So basically, it will be more penalized if there are more changes to its updates. And less important parameters have a more flexibility to be changed. On the other hand, we have feature prediction space. That is regularization at the features and the predictions regarding past data, so that they do not suffer significant changes. And usually in this case, what we basically do is we train the data, and then we have a model, then we have the new data. But before, basically we just create a copy, and we have a copy of the model, and then we use that model to distill this knowledge for the new one. A big disadvantage of this process is the non-scalability, because as basically if we have too much concepts to learn, what basically we are doing is that as new data is arriving, we'll lose the level of plasticity, and so basically there will be no acquisition of new knowledge. Then we have dynamic architectures, that are strategies that extend the structure of the network by adding resources. And these resources can be layers, modules, or even neural networks. These resources will be associated with a new task, class, or domain. In addition, there are also some strategies. These could somehow could be similar to regularization in the sense that they strive to identify elements of the network that could be repurposed for the acquisition of new data. A good thing about this strategy is that it may prevent the catastrophic forgetting effect in the sense that when we are adding these resources, basically just they train that specific resource for specific data, and then when new data arrives, that specific resource will not be updated, so it's frozen. But on the other hand, we could also have non-scalability in the sense of if we are expanding indefinitely the networks. Apart from that, if we are assigning specific resources of the network to specific class domains, we will need an identifier. For that, we could use an Oracle identity, but that will also be what we need to be continually trained. And finally, if on one hand, this may prevent catastrophic forgetting effect, on the other, it may not promote transfer knowledge, right? Because if these modules are frozen, then they may not be benefiting from the acquisition of new data. And finally, we have the experience replay methodologies that are inspired by our capability to basically consolidate memories through the replay of those memories. And so in this case, these strategies store in memory in a very buffer past data that is then interleaved with data from the current experience during training phase. So regarding the selection of the data, there are several methodologies. First, regarding the buffer size, the memory buffer, there are two types that can be, two strategies that can be followed, either to have a fixed size or to just not define it, just have a ever-growing buffer. And then regarding the data selection, we could also have a random sampling of the data, or instead just apply a metric in order to select what samples we want to add. And finally, the type of data that we want to store. We can have the original data, or we can have generative data. The main advantage of experience replay methodology is the better ability to cope with the catastrophic forgetting effect. Literature shows that experience replay are the best to cope with this effect, but there's a downside to it. So basically, this method really depends on storing past samples, and we could not have the resources to allocate extra memory. There are also financial and computational resources. And there's the additional challenge that is, especially in the medical domain, we cannot store raw data, right? So we could use generative replay, but there's a problem also with generative replay similarly with that Oracle with the dynamic architectures, is that this generative replay also needs to be continually trained. And finally, what is missing and where to next? So basically, we saw, I show you all the continual learning scenarios, right? There are 4 types mainly, but one thing is missing to the discussion, and that is the study of the learning order. So basically, some of the papers do present do study different learning orders and present what's going to be the best one. But usually there's an explanation lacking on why specific learning order is better, and especially if you think that these methods are developed in a controlled environment. But what happens if then we go to a real world application, or that is much harder to control. And also we have the continual learning scenarios. Some of them do not reflect the reality in the sense that when there is a restriction of no repetition, because in the real world there is going to be repetition. One cannot control what type of data it will see. And finally, we have the supervised settings. Most of these approaches were developed in a supervised setting, but we know, and especially with the medical domain, that the majority of the data is not labeled, and as such, we should move towards other algorithms that can cope with the unlabeled data.